Holy smoke. So this is one of those things I've kind of written on that syllabus for years, admittedly somewhat cavalierly. Yeah, just do problems 9 through 48. These are important problems. We're gonna have to do these types of problems really throughout the entirety of this whole course. So it actually is really important for us to really kind of make sure that we can do them well, and we can at some point kind of do them without even thinking about them. That said, I don't know that I really appreciated how much 9 through 48 was until I finally forced myself to sit down and kind of go through and do all these problems myself. But again, right? If it's if I'm going to expect you to do it, then I probably should expect myself to do it. I was very tempted to just change the syllabus and say, well, why don't you do problems 9 through 13? That sounds more reasonable now. That would save you and I both an awful lot of work. Particularly when, as you may or may not have already realized, many of these problems actually are sort of four-part problems. So 9 through 48 is actually, I think, pushing maybe like close to 100 actual problems that we're doing. That said, right, they do go pretty quick once we've hopefully figured out the pattern. And I kind of leave it to you. Do you really need to do all 100 of these things? Probably not. But I do want you to make sure that you do a lot of them. And I do want you to make sure you hold yourself accountable. And I do want you to make sure that you don't stop until you really, really do feel like it's sort of become like a nauseating waste of your time. Until then, until that point, remember, homework problems are how we invest in ourselves. Yeah, I like that. Homework problems are how we invest in ourselves. So let's invest away. All right, first few problems are kind of fill in the blank. So, right, if you actually read this problem out of the textbook, every place where you see a bold-faced word is actually just a blank in the textbook. So the bold-faced word is me filling in the blanks. So number 9 is just saying the proportion of a population contained within an interval corresponds to an area under the probability curve. So that's just like a fancy way of saying um, that we think of from this point on. It's really a powerful idea. We think of we think of area and probability as being synonymous concepts. Number 10 is kind of emphasizing a quirk of continuous random variables. So, right, all of this chapter 7 is working with something called a normal random variable. The normal random variable is just one type of continuous random variables. And for all continuous random variables, the probability that they equal any specific number is always 0, right? It kind of ties into point 9. Point 9 said we think of probability and area as being synonymous. The probability x equals a is just like a line. If we were to draw that under that normal curve, it would just be like a line at the point A, and lines have no area, hence we can think of them as having no probability. I actually often put a question like this on the exam, right, where I say like the probability that like x equals 12, what is that? And the answer is exactly 0. It's not sort of 0, it's not close to 0, it's not 0.001. It's a math fact that that probability is exactly 0. Little unintuitive, but nonetheless true. Number 11, the area under the entire probability density curve is equal to 1. So you can think of that 1 as like is representing 100%, right? So everything is under that curve, right? All 100% of our probability is contained under this density curve, of which we've seen some pictures in the narrated PowerPoints, and there's of course some more pictures coming up in these PowerPoints as well. Um, Number 12, for a normal distribution, because it's symmetric, the mean, the median, and the mode are all the same. So the mode is just the peak of that thing. So we're basically saying that the peak of this distribution, right? The normal distribution is that very classic bell-shaped distribution, right? So the mode is always like the peak of the hill, the top of the bell, and that turns out that's also the mean, it's also the median. Remember, the median is defined as that 50th percentile. So right, that middle point right at the peak sort of splits that area in half, 50% to the left, 50% to the right. Number 13, just a definition question. A normal distribution with a mean of 0 and a standard deviation of 1 is called the standard normal distribution. It's often abbreviated with the letter Z. Number 14, points on the horizontal axis to the left of the mean have negative Z-scores, right? So again, we're talking actually about that standard normal. If we draw that standard normal, the center is 0, everything to the left of it is negative, everything to the right of it is positive. A little bit of true false. So number 15, the probability that a randomly selected value of a continuous random variable lies between A and B is given by the area under the density curve between A and B. Again, reinforcing this idea that probability and area are synonymous. We can represent this abstract idea of probability with the more concrete, see it with our own eyes, notion of area. So that's true. Number 16, a normal curve is symmetric about its mode. That's true. Kind of already said that. Number 17, a normal curve is wide and flat when the standard deviation is small. That's false. It's actually when the standard deviation is small, that means that there's very little variation. Actually, that normal curve is tall and skinny. So small standard deviation means tall and skinny. Wide and flat means that it's very dispersed, it's very spread out. There's a lot of variability, a lot of variation, so it has a large standard deviation. And then number 18, the area under the normal curve to the left of the mode is less than 0.5. That's false. It's actually exactly 0.5. So remember, the mode is the median. Median is the 50th percentile. That means the area to the left is exactly 50%. So here's a couple problems reinforcing this idea of area and probability being synonymous. So this is an alleged density curve, which represents the lifetime in months of a laptop battery. So how many months your laptop battery is going to stay alive. Now notice this is actually not a normal curve. This one looks like it's got a little bit of a right skew to it. And so when we say that this random phenomenon has this density curve, what does that mean? It means that that if we bought a bunch of laptops, hundreds and hundreds and hundreds of laptops, and we recorded how long it took for each of their batteries to die, so we have hundreds of battery lives, and we made a histogram, right? So histograms are harkening back all the way to chapter 2. We made a histogram. We're just saying that the histogram is going to have this type of shape to it. That's all we're saying. And so the first question is, find the proportion of batteries whose lifetimes are between 12 and 18 months. And so the book actually kind of colored that in for us already. So we look at that area between 12 and 18. The book tells us that area is 25%. We can think of area and probability as being synonymous. So if that area is 25%, it's saying that 25% of all batteries have lifetimes between 12 and 18 months. Yeah, pretty straightforward, right? What proportion of batteries have lifetimes less than 18? So we have to look all the way left of 18. So we actually have to add together the 25% that's between 12 and 18, as well as the 35% that's to the left of 12. So we add 25 and 35 gives us 60%. So 60% of all batteries will have a lifetime less than 18 months. And the last question, what's the probability that a randomly chosen battery lasts more than 18 months? So that's actually would be the area to the right of 18. It's not colored in the picture. It's actually the white area that we're interested in. So how do we find that? Well, we use that little fact that we had in a previous slide. That fact we had in the previous slide said that 100% of the area is under the entire curve. So all the area under the curve is 100%, or 1. So if we know that 60%, we found this out in part B. If we know that 60% is to the left of 18, then 1 minus 60% will be to the right of 18, right? I mean, the math sometimes can feel a little bit convoluted, but I feel like it's a little bit like we're used to that kind of logic, right? If you say there's a 60% chance that your battery is going to die within 18 months, we'd say there's a 40% chance, 1 minus 60, that it's going to live longer than 18 months, right? That's all we're saying. But where does that rationale come from, right? We're seeing that rationale maybe a little bit more explicitly or maybe a little bit more clearly than we're used to. Number 20, again, not a normal looking curve. This following curve is the probability density curve representing GPA of graduating seniors at a large nameless university, may or may not be Westchester University. Yeah, go Rams. So find the proportion of seniors whose GPA is between 3 and 3.5. Again, the book just colors that in. It's just it's as straightforward as saying, like, okay, the book tells me that area is 24%. Area and proportion, area and probability are synonymous. So I'm going to say 24% of all seniors have a GPA between 3 and 3.5. What's the probability that a randomly selected senior will have a GPA greater than 3.5? This is kind of like part C from the previous problem. First, we have to look at what's the probability of a senior having a GPA less than 3.5. So to find the probability of having less than 3.5, that's going to be the 24% plus the 67%, 91%. So if 91% of all seniors have a GPA less than 3.5, then 1 minus 91, or 9% of all seniors, will have a GPA of more than 3.5. So if your GPA is 3.5 or more, congratulations, you're part of the 9%. And if it's less than 3.5, well, who knows? Hopefully you're not a senior, and if you're not a senior, then there's still time to get that GPA up. Starting with Math 121, right? How would an A in this class sound? Pretty good, right? Yeah, keep doing the homework problems, and you're going to get there. All right, here's these 4-part problems that I was warning us about. So now we're going to get a lot of practice with our calculator. All right. So again, I really encourage you to do these problems on your own first, and then I'm actually going to try to kind of pull back how much I just like to to go on and on. I get very passionate and very excited about statistics, and these narrated PowerPoints drag on and on because of it. I'm going to try to just kind of just boom, 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 go through these slides quickly, so you could just use them to check your answers. Again, you should grind through all these problems on your own, and then just be using these narrated PowerPoints as just like a way of checking your work. The book draws the pictures for us here. And we can see there's really kind of like 4 types of problems. I would kind of argue C and D are kind of the same type of problem. So if you're going to buy into that, there's really just 3 types of problems. Right? The first is kind of like the probability of being less than some number, or the area less than some number. For all of these, for all normal probabilities, we're going to use that normal CDF function, right? So for all of these problems coming up, it's going to be normal CDF, which we can find in our TI calculator under, we hit the second function button, then we hit vars, and then we go to the normal CDF function, right? And so there's four things that it expects, right? A left bound, a right bound, a mean, and a standard deviation. For this whole PowerPoint, that mean and standard deviation, they're all these Z distributions, right? So these Z distributions, moving on, are a mean of 0 and a standard deviation of 1. So we're going to be putting 0 and 1 in for those last two slots over and over and over again. The Z distribution is like a little bit weird. It's a little bit artificial. It's a little bit tricky to work with because it's so important to the application of statistics, but it'll take us a while to see that and to see why that is. Until we get there, it's just this kind of weird, kind of arbitrary kind of feeling thing. Like, what kind of random phenomenon has a mean of 0 and a standard deviation of 1? Makes it hard for us to put it like in the context of an actual problem, which for me, it's always easier when it's in the context of an actual problem. Again, I always kind of argue, maybe just think of it as like a bizarre test where maybe you actually lose points if you get a question wrong. And so because of that, it's possible to get like negative points on this test. And we'll say like on average, people get a 0 on the test. And then we could just think of this in terms of that test. So like this part A is kind of like what's the probability of getting 1.25 or lower on the test? And so we do that normal CDF, right? Our leftmost bound in theory goes on to infinity. There's no infinity button on our calculator, so we do that -1 e to the 99. I talked about that in the narrated PowerPoints. If you're not sure about it, go back to them. But I go -1 e to the 99. That's really just saying like -1 with 99 zeros after it. So that's like a really, quote, big negative number. Like negative a jillion. So normal CDF, negative a jillion. The rightmost bound is 1.25. That mean and standard deviation for this PowerPoint, right? We're working with these standard normal curves. These Z curves is always going to be 0, 1. Put all that in your calculator, 8943. Sorry, 0.8943. Second type of problem, right? Probability of it being greater than some number. So what's the probability of getting 0.36 on this test or higher? Well, now our leftmost bound, our lowermost bound is 0.36. Our upper bound, in theory, we don't have one. In theory, it goes all the way to positive infinity. There is no positive infinity, so we put 1e99. That's like 1 with 99 zeros after it. So that's like positive a jillion, right? So normal CDF, 0.36, a jillion, the mean of 0, standard deviation of 1. Verify that you get 0.3594. Third type of problem is what's the probability you get between two numbers. So what's the probability you take this test, you score between -0.71, positive 1.62. Actually, this is, I think, the easiest to do on the calculator because you don't have any of those like e to the 99s to worry about. Leftmost bound, -0.71, rightmost bound, 1.62. Again, working with that Z thing, that's standard normal, so the mean is 0, standard deviation's 1. Plug all that in your calculator, verify you get 0.7085. D, you want the area like in these little tails. And so to find that, again, we use the fact that the entire probability is 1. And so actually I say just find the area that's in the middle and then just do 1 minus that. Hopefully that makes sense, right? So it's kind of like a part C problem. We're finding the area between -0.28 and 0.94 and then removing that area, right? So we find out what that area is and then we remove it and we're left with just the area and the tails. So we take the total area, which is at 100% or 1, and we subtract from it that normal CDF, -0.28, positive 0.9401. That's the sort of area in the middle. We remove that, we subtract that. That area is 4367. So like 1 minus like 43-ish, 44-ish% gives us about 56%. Okay, so I talked through it maybe a little fast. Hopefully you got those answers. If not, it's not a big deal. Try the next problem. Even if you don't get that right, listen to me talk you through it, and then try the next problem and the next problem until finally at some point, I promise you, it will click. Number 22, actually 22 is pretty much the exact same, right? It's the exact same. Starts with a less than problem, then a greater than problem, then an in between two numbers problem, and then a two tails problem. So again, you solve it in the exact same way. Anytime it's less than, you put that -1 e to the 99 in the leftmost bound. Anytime it's greater than, you put that +1 e to the 99 in the rightmost bound. Anytime it's between two numbers, you're not going to have an e to the 99. And anytime it wants those sort of two tails, you're going to do 1 minus what's in the middle. And then the book just does a bunch of repetitive problems. It's just asking the same thing we've already solved, just in slightly different ways. So now instead of showing you a picture, right, the actual question doesn't have the picture. I drew that picture in. The actual question just says, find the area under the standard normal curve. Standard normal curve means mean of 0, standard deviation of 1, to the left of z equals 0.74. So that's the question. I drew the picture there. I drew the picture to help us see what's going on. Once I draw the picture, I see that, oh, okay, that's the type of problem where I want all the area to the left. So that's where I do. If you look under the picture, I tell us the syntax in the calculator. Normal CDF, -1 e to the 99, positive 0.7401. So go ahead and plug that into your calculator and see what you get. And then B, C, and D are all the exact same type of problem. So, right, verify all those answers, right? I drew that one picture. All the other pictures are going to look essentially the same. And then 24, A, B, C, D, more of the same. All the same type of problem. 8 examples of the same type of problem. Enough practice to keep an octopus busy. And then now the book switches it, right? So now it's doing a bunch of examples of area to the right. So it says find the area under the standard normal curve to the right of z equals -1.55. So again, I drew that picture. So I read the question. First thing I do, I always draw a picture. A picture is my best friend. Standard normal curve is centered at 0. -1.55 to the left. So I go over to the left. I draw that. I want everything to the right, so I color that in. Right, drawing the picture and coloring it in, it helps me and hopefully helps you, because I could look at what's colored in and I could tell you right off the bat. I don't know exactly what the answer is without plugging it into my calculator, but I know that answer is going to be more than 50%. More than 50%. Right, why? Because I mean the area to the right of 0 is 50%. And this has all of that area plus a little bit extra, plus the area between -1.55 and 0. And so there's a lot of ways to plug something wrong into your calculator, but a lot of times it'll give you kind of like the opposite answer. So like most wrong ways I plug it into my calculator will give me an answer that's smaller than 50%. And as soon as I see an answer that's smaller than 50%, that's like an instant red flag. And I get a little bit more serious. I scrutinize what I did. I find the problem, I fix it, and I don't rest until my answer is something more than 50%. So in this case, the syntax is written below the curve. Normal CDF, -1.55, 1 e to the 99, 0 and 1. Now again, Not surprisingly, 95B, C, and D are all the same type of problem. So again, pause this if you haven't already and do B, C, and D on your own. Try them. You are not going to learn how to do it by just sitting here and passively listening to me do it. You're only going to learn how to do it if you do it yourself. So if you haven't already, pause it and do B, C, and D. Draw the picture. When you draw the picture, ask yourself, is the answer going to be more or less than 50%? And then solve the problem and verify that you're right. Get the actual exact answer. And of course, I'll show you the exact answer on the next slide. Once you do that for B, C, and D, then go ahead and do it again for 26, same type of problem. So there's going to be 7 problems that are pretty much exactly like this one. Go ahead and do them. So there's the answers, hopefully the same as what you got. And then here's some more answers, hopefully same as what you got. All right, third type of problem, area between two numbers. So again, right, it just, the question itself just says find the area under the standard normal curve between negative 0.75 and 1.7. I then took that and drew the picture. So that's what the picture looks like. These are, again, I think, using the calculator, the easier types of problems, because I don't have to worry about that e to the 99 silliness. My leftmost bounds very, very clearly negative 0.75. My rightmost bounds very, very clearly 1.7. Again, standard normal means I put a 0, 1 at the end there. Plug all that in, I get 0.7288. So, right, again, not surprisingly, B, C, and D, same type of problem. 28, A, B, C, and D, same type of problem. So you got 7 problems that fit the exact same framework. If you haven't done them already, go ahead and do them. Make sure you draw the pictures too. All right, there's the answers. And there's some more answers. All right, last type of problem. Find the area under the curve that lies outside the interval between negative 0.38 and 1.02. So again, this is like finding the area between those and then doing 1 minus. So it's exactly what I have below there. 1 minus normal CDF, negative 0.8, 1.0201. So it turns out that's actually really, really close to 50%. So again, if you haven't already, pause it, B, C, D, and then all of 30 are all the same type of problem. So again, right, just do that same type of problem over and over until it finally starts to kind of sink in and stick. Hopefully same answer as you got. Hopefully same answer as you got. So 31 is where the book kind of starts to mix it up a little bit. So the actual question from the book just says, find the z-score for which the area to the left is 0.54. So this is actually, the book's a little bit kind of indirect with its language, but this is actually just asking us to find a percentile. Right, so I kind of drew the picture. It's a little different than the other one. Here the book gives us the area and it wants us to find the z-score, right? So I wrote up on top the 54, that's the area. And then I put a little question mark. Notice I know, and hopefully this should make sense. I know that the answer for question mark is going to be positive, right? Because the center is 0. So the area to the left of 0 is 50%. So to get 54%, I got to go a little bit out to the right. And of course, out to the right means a positive number. So my answer is probably going to be pretty close to 0, but it's going to be positive. Now I find percentiles using the inverse norm function, right? Inverse norm, because it's like the inverse, it's like the opposite of the problems we were doing. The problems we were doing before, right? I gave you a z-score and I asked you for a probability. Here I'm giving you a probability, I'm asking you for a z-score. The syntax for inverse norm is PMS, percentile, mean, standard deviation. Again, for this PowerPoint, we're gonna be working with those standard scores, those z-scores. So the mean and standard deviation is gonna be 0 and 1. So it's just the percentile. Percentile is defined as area to the left. So that's the literal definition. So we just we want area to the left is 54. That's the exact same thing as telling me the 54th percentile. So I plug all that into my calculator. I get the answer 0.1004. So it's basically like saying 54% of the class scored less than 0.1004 on this weird, bizarre test that I've kind of made up to make this thing a little bit less abstract. 32, 33, and 34, all the same type of problem. They all ask for area to the left. Area to the left is just the percentile. So we're finding the 13th percentile, 93rd percentile, and 25th percentile. Then the book asks for the area to the right. It says find the z-score for which the area to its right is 84%. So I drew that in, right? 84% to the right means it's going to be a negative number. It's going to be to the left of 0. Now our calculator, unfortunately, it only does area to the left, right? So I can only find area to the left using percentiles, but I guess at least right off the bat, I don't know the area to the left. I know the area to the right is 84%. But that just means the area to the left is 1 minus 84%. Do we agree? So 1 minus 84% is 16%. So again, classic mathematical technique, right? I take something that I'm not sure how to solve, and I re-express it in terms of something I do know how to solve. So the area to the right being 84 means that the area to the left is 16. So I want to just find the 16th percentile. Once I know that, I could just plug 16 into inverse norm. So if you look down below under the curve, you're right, I write 16% as 1 minus 84. You can actually put that in the calculator that way. You can say inverse norm. You can literally write 1 minus 0.8401. And that's going to essentially find the 16th percentile for you, which is negative 0.99. Now again, right? 36, 37, 38, going to be all the same type of problem. So, right, pause it and solve them. And then once you've solved them, check your answers on the next slide. So again, 14% to the right means 86% to the left. 35% to the right means 65% to the left. 92% to the right means 1 minus 92, or 8% to the left. The last ones are maybe like concept checks. So I'm hopeful that by now you've drawn all the pictures, you've used all the calculators. Like, you don't really need calculators for these problems. It's really just sort of recognizing the symmetry. And so at this point, I kind of leave it to you to draw the pictures. If you can't draw the pictures, if these things, after all that work, still don't make sense, it might be worth coming in and talking to someone. I'm hopeful that they do. But if not, you should, again, hold yourself accountable. Come talk to me during my office hours. Right, we have graduate assistants in the math building in the evenings or kind of late afternoons. They could help you. Of course, there's also tutoring at the LARC, the Learning Assistance Resource Center. So I'm pretty confident you know the answers and you understand where they're coming from. But if not, it's a good concept check as to maybe you should come check in with someone and do a little bit of one-on-one time with someone. Right? Hopefully these narrated PowerPoints help, but they're still not really a good 100% replacement for like actually kind of like face-to-face time. So I'll leave it to you to kind of convince yourself if the area under the standard normal curve to the left of negative 0.175 is 4%, then by symmetry, The area to the right of 1.75 is also 4%. Incidentally, you should be able to use your calculator to verify that, but we don't need to use our calculator, right? Because if left to negative 1.75 is 4%, then because of the symmetry, we know that to the right of positive 1.75 has to be the same thing. And then 44 through 47, same idea, just a bunch of symmetry questions. So I'll leave it to you to kind of draw the pictures and convince yourself. And last one, I went ahead and drew a picture. Let A be the number such that the area to its right is 21%. Without using table or technology, find the area between negative A and A. So A is just some number. We know to the right of it's 21%. So by symmetry, the area to the left of negative A is 21%. That's hopefully what we just reinforced with the last few problems that we did. So again, total area is 100%. We have 21% to the right, 21% to the left. So the area in the middle is that 100% minus the two 21%, minus the 21% to the right, minus the 21% to the left. So minus what? Minus 42%, right? So 1 minus 42% is going to be 58%. So that area in red is 58%. Right here, we're trying to move a little bit away from the calculator and trying to actually build up like a little bit of like a little bit of, I guess, not so much number sense, but like probability sense, right? So we could actually internalize, like, not just like blindly putting numbers into a calculator, but kind of really understanding like what's going on with these sort of pictures. All right, that was a lot, but if you made it through, then great job, and and your reward is going to be another barrage of practice problems from 7.2. But why don't you go ahead and take a break, and then afterwards I'll see you there.